Hey, everybody. Just wanted to follow up on some of our conversations about probability. We've talked a little bit about conditional probabilities when we look at our pedigree analysis, and we'll talk a little bit more about them in another slideshow we've got talking about the paradox of the false positive. But right now, I want to talk a little bit more about how to do certain calculations and actually define and calculate precisely the odds of particular combinations occurring. And obviously, this is very helpful if you're out playing any of the gambling games in Atlantic City. And you'll find that doing the calculations sometimes goes counter to your instincts. Okay, people are notoriously bad about figuring out math problems instinctively, so that's why we have to learn how to do the calculations. Notably, a very simple example that we have is just again flipping coins. And flipping coins is a great thing to do in genetics because very often we have the possibility of a single gene with two alleles. And in this case, we have a single coin with two possibilities, heads or tails, two sides. And so what we really want to know is what is the probability of getting all heads or all tails, or three heads and one tail, two heads and two tails, one head or three tails. Now, on the surface, this seems fairly obvious. But in order to do the actual math, to do the work, what we really need to do is to recall some of our definitions from our conversations about probability. Here's a brief reminder. Again, when we talk about figuring out probability, we are really talking about doing a random experiment. This is our observation of any outcome of a chance event. And the two definitions you always need to keep in mind are what are the elementary outcomes and what is the sample space. So, an elementary outcome is just all the possible results of any given experiment or trial, and the sample space is the collection of all of the elementary outcomes. So let's try to apply some of these ideas in our existing problem. Now, what we really want to do is think about this idea of flipping four coins, okay? So our elementary outcomes are really simple. It is what are the possible results? Well, it's either heads or tails. Not hard. What's the sample space? That is, what is the collection of all possible outcomes? So if we're flipping four coins, there are two possible outcomes. So what's the possibility of two outcomes and two more outcomes in coin 2 and two more outcomes in coin 3 and two more outcomes in coin 4? Recalling the rules of probability, anytime we use the and word, we know we multiply. So our total sample space is 16, or 2 times 2 times 2 times 2, or 2 to the fourth, however is easiest for you to think about it. So obviously, it's really easy to count. So here are all of our possibilities. All heads at the top, all tails at the lower right, and of course, all of the other possibilities along the way. So, what then are our relevant outcomes? We now know our elementary outcome. We know our sample space, which was on the previous slide. So, what are the relevant outcomes? The relevant outcomes are based on the question that we asked. That is, four coins are flipped. What's the probability of each coin being heads or tails? Okay? Very easy to figure out. Well, there's only one way because each of the elementary outcomes, there is a 50% chance of either heads or tails. And if we've got the probability of heads and heads and heads and heads, and I think one more heads, 4. Okay, the probability of 4 heads is half times a half times a half times a half, or 1/16. So that part is pretty easy to do. The difficulty comes when we think about 4 coins flipped. What are the probability of there being 2 heads and 2 tails? Well, we can't multiply half times a half for heads and then half times a half for tails, and then what do? Do we multiply? Do we add? Do we divide? It becomes a more difficult mathematical problem. Now, the reality is it's super easy to count. And if we think about 2 heads and 2 tails, and you look at our notation here in the slide, notice that in the red, everything red is 2 heads and 2 tails. And so we see out of our total possible sample space of 16, there are 6 out of 16, or 3/8 of the possibilities that conform to our relevant outcome. But the calculation requires a little bit different solution. And this requires our knowledge of the binomial distribution. Okay? So in this case, we need to estimate the total number of relevant outcomes. And the correct formula takes the form of this large set of brackets with 2 heads, that is our relevant outcome, 2 heads on the bottom of the brackets, and at the top is the total number of actual flips. So we've got 2 heads out of 4 flips. And in order to show you the mathematical expansion, the calculation is very, very simply the total number of flips, which is 4 factorial. Remember, 4 factorial is just 4 times 3 times 2 times 1. It is all the integers below the numerical value of n, times k factorial, or divided rather by k factorial, times the quantity n minus k, again factorial. So in this case, pretty easy to do the math. We know that our relevant outcomes are 6, okay, and I'll let you do the math yourself. So we now have to divide by our total sample space, and we know that the relevant outcomes divided by the sample space is 6 out of 16, which matches the total number that we actually counted. And of course, this equals 3/8. So pretty easy to do. However, what you may recognize is this is related to Pascal's triangle. And these are series of binomial expansions, or the binomial solutions. And of course, Pascal was the first to realize that when you have a quantity added together, x plus y, the quantity raised to a power function, whether it's 0, 1, squared, cubed, to the 4th power, the 5th power, what he recognized was that the integers that prefix, or the multipliers of each individual combination, followed a pattern. And he looked at it like a triangle. So of course, x plus y, anything to the 0 power is 1. X plus y to the 1 is just 1 times x plus 1 times y, and we see that across here. And now when we have x plus y squared, guess what? 1 to 2 to 1. Does that look familiar to you? 1x squared plus 2xy plus 1y squared, 1 to 2 to 1. And of course, he recognized very quickly that he could fill in the rest of the triangle not just by doing the multiplication of a quantity, but rather he found he could add each of the integers and they made the integer below. So this is called Pascal's triangle. If we were to look at it in terms of our combination, what we could do is show each of these rows indicating the formula with brackets and combinations, and notice we have the same distribution of multipliers as in the previous slide. So the reality is some of the questions that we ask are rather simple, and you can certainly do 1 to 2 to 1 or count 6 out of 16 possibilities in your head. All right? But you should always certainly learn and always get used to using and applying the more sophisticated and elegant method. Why is this? Well, it turns out in genetics, this is extremely important because we're not only going to deal with 4 possibilities of either heads or tails, and if you think about an individual coin toss as a gene, and a heads or tails as 2 possible alleles from that gene, again, 4 genes, each having 2 alleles, pretty easy math to do. You can draw it out, you can sketch it on the margin of a notebook paper, and you can figure it out quickly. But what happens when you want to look at 20,000 genes, each having 2 or even more alleles? Okay, the math becomes much more difficult, and so we have to learn the more technical skill of actually calculating combinations and total sample space. Now here's a problem for you to solve on your own. Remember, we talked about our black and white guinea pigs, black coat color dominant to white hair. And you recall our conversation about how that was one of the most important problems because it illustrated several different sets of concepts that we had. So I'd like you to go back to that problem. And in a mating of 2 heterozygotes, remember this would be a cap B small b crossed with a cap B small b individual. Well, what frequency would you expect to find 3 white guinea pigs, 2 blacks, 2 whites or 3 blacks, 1 white and 4 blacks, or all white guinea pig? Go back and think about how you can apply the binomial expansion to the original problem and the original question asked in that problem. It's an easy little exercise. You ought to be able to do it in just a couple of minutes. An important one because you may just find a very, very similar question and application of the binomial expansion on the next exam. Take care, stay safe. See you in a bit.